Hello, everybody. I'm Shri. I work at the Max Planck Institute, as Kurt introduced. I work with Max from the Institute in Garching. And today I'm going to talk about big data in astrophysics, so to say, and why we need a tool like iNode. So to start with, we all know that, we are in the era of big data, and astrophysics is no exception. We have so many astronomical surveys, meaning that, various telescopes around the world are observing the sky every night throughout the year. And we call that as a survey. And, there are so many current surveys like SDSs, headaches, and so on. And there are so many surveys which are coming in the years, like in couple of years. At the same time, we have these open questions existing in the field for kind of decades now, like how the universe began and how it's going to end, or we are in the Milky Way galaxy. It's one of the galaxies out of the billions in the universe, and how these galaxies form or how they evolve. And there are so many questions like like the structure of the universe, how it is, and so on. What we now know that data is our new treasure, and we need a right kind of tool to leverage this data properly in such a way that we will be able to answer the questions existing in the field. And as I said, like different telescopes are observing. They are not only observing in the visible light. That means what you can see with your naked eye is a visible light, but it observes in different wavelengths throughout the entire electromagnetic spectrum, from radio and to gamma rays. So we have huge amount of data piled up. And one such survey that we use for iNode is the Sloan Digital Sky Survey. It started back in the year 2000. So we have wealth of data over the last 22 years. It's not the end. We are in the fifth phase of observing, and over the years they have also implemented the new technologies, new instruments, and new way of observing everything. So it's a very interesting database. And over these 20 years, more than 20 years, it has already produced the most detailed three-dimensional map of our universe. And when I say that, we observe with the telescope, that means like, there are two kinds of observation. We see it like a photo, it's an image of the astronomical object, but otherwise, we also study the amount of light emitted over the wavelengths in the electromagnetic spectrum, and we call that a spectrum. So there are two kinds of observation people normally do. And for example, with our Sloan Digital Sky Survey, also called as SDSs, we use the fourth, data release version 16, and to give you an idea about what kind of number of records that we are handling, it's of the order of 800 millions here. And when we have this kind of huge amount of data, we also have databases associated with them. And normally every astronomical database would have three kinds of categories of tables, like photo group of tables where you have information from the images, and then spectral group of tables where you have information from the spectrum, and you also have meta tables with all the information and documentation about the project. So there are so many, to say, not just SDSs, there are quite a few astronomical databases around, and they all use the relational database management system. For example, in SDSs with the data release version 16, we have 128 tables, and also like views with important attributes. So when you have this kind of databases, what are the problems? Like, you have the database, you have your own user interface. It's a data exploration tool where you can explore the databases. But the problem is one should be an expert in the database language like SQL or and then you should have a good idea about the schema, and you should be very precise on what you want from the database. And if you go to the data or the tables in the database, like you should know the schema or the foreign key relationships, and which are very difficult because astronomers not only use one astronomical database for their research, but they tend to use multiple astronomical database at the same time. And it is very difficult to kind of include or link other databases and to derive a lot of interesting objects, or like, it's also difficult. There is no explanation of what the results you get from such exploration tools. So let me go into the use case example. Here you see the green pea galaxy. Yeah, it's called the green pea galaxy. These green dots that you see here, these objects were identified in a citizen science project called Galaxy Zoo. Means like, in this project, common people would be asked questions to identify galaxies and classify them with examples. And when some people stumbled upon this, different, entirely different kind of objects which are green dots, and they gave them green peas. And once a few of these green pea galaxies were identified, nobody knew at that time that they were galaxies. Actually, they were just green dots. And then astronomers got very interested into this new kind of object, which they never observed before or analyzed before. And they started looking into them from in imaging as well as in spectrum. They studied them extensively, those few objects identified, and they kind of categorize their imaging properties, like how bright they are or how big they are in the images, and also from the spectrum, from which kind of emission line are emitted by these objects. And one should write extensive SQL queries like the one in the left, with all the information which astronomers kind of derived over kind of year of analysis, and try to query a database with such kind of SQL queries, and in getting more similar objects, so to say. So they started studying tens of objects, and then using this SQL query, they identified 250 galaxies. So these galaxies also have analogs, so to say. Depending upon how far the object is in the sky, you see different kind of properties in the images, like colors, or in the spectral lines as well. So analogs are similar objects, but at different distance and in the sky from us. And for example, there are blueberry galaxies and luminous compact galaxies. We believe those are analogs because they share the similar properties, but they are just, they look kind of little different in the images. So what we need actually is as a very good tool in which one should be able to easily access databases, and then the attributes are not abstract in such kind of tools, so that we understand it properly, and also the tool should allow us to incorporate new databases in the future, and it should also provide you a kind of visualization of what you are looking at, and it would be great to have recommendations as well in the astronomer's point of view. And that's what our, so to say, our goal also with inode. So thank you so much.